this is the scattering cross-section. Then you just try to produce the radical density. Then you're in business to say, well, I produced 27% of the energy budget in the model. Okay. But then, of course, when it comes to the direct detection, then is the dark matter and the emit Higgs, and then Higgs hit the target. And of course, so this slide, you know whatever the parameter is. And then Higgs coupling to quarks, and then you can do some model calculation, pair of division theory, or some homological matrix element. And then you can get something in this sort of a range. So then by this, then you can know what it might be the scattering cross-section of dark matter with the target. Okay. So once you have this, then you can do the detection sort of a limit, or how you might detect it. But of course, now we also said that a PP collider might be able to produce Higgs, and then Higgs may decay. But if Higgs decay, if the dark matter mass is less than half of the Higgs mass, then this decay might happen. This decay might happen, but then of course, at the detector, you don't see Higgs decay to two dark matter, then this becomes invisible or decay wave. So then you can use the property of Higgs invisible wave to constrain whatever is allowed as parameter space. So if it's like this, the branching ratio of Higgs become sort of invisible, become very big. So right now it's about 60%. So if only very close to the threshold is allowed. So you can then constrain your model. Okay. So now, if you come back to the simplest one, then you do this radical density sort of fitting. Then you find that there's a lambda, the parameter interaction of Higgs with the dark matter. Then it goes like this sort of thing. Now, there is a deal in this because this is at the resonant point. The Higgs mass is about 2 times the dark matter mass. So a very small sort of a lambda interaction become have a larger cross section. So that's why you have a very small lambda, you can also produce the radical density. And then this here. But then of course, when this lambda becomes too large, maybe you can have unitarily constrained. Your theory is not repeating the thing. You say, well, maybe I should stop there. It's not sort of safe, or whatever prediction you make. Maybe it's very questionable. So then you can also count it at some of order 1. So this is the sort of thing. Now you notice if I put in the experimental observation and translate it into this, then you find all from here to here is ruled out. And then of course LHC, you can look at the Higgs, say if you have a dark matter with invisible waves, then this is ruled out. So only very close to the threshold is allowed. Now, if you translate it into the cross section, then this is usually say in the plot. And then the hand X is over here, Lux is here, and then so from here to here, this model is not ruled. So that means if you translate this into the mass of the dark matter mass, then between 450 GeV to about 50 GeV is ruled out. Okay, it's ruled out. And then also you notice in the future there are several other experiments, LZ and Z-Tom and some others. So then they can make it further down here, and then you might rule out more parameter space. And then notice here is a so-called neutrino flow, or sort of thing. And then when the sensitivity becomes bigger and better, you may reach the neutrino flow. And so that means you have background the neutrino from the sun, from the earth, whatever. And then when you go below the neutrino flow, it's very difficult for dark matter research. So your background, everything become mixed up. But now, of course, at this stage, people are already worried about it. If indeed we reach the neutrino flow, what do we do? So people are thinking maybe you have a directional or sort of thing. So because our Earth is in the solar system. Solar system is sailing in the galaxy with a certain direction, and then maybe dark matter, if it hit us, maybe some have some direction of thing. Then people starting to worry about it. But then before that, then people are just for some signals. And then now you notice here the Higgs mass or Higgs decay rate is very important. Whether it's about the neutrino flow and you know the neutrino flow for this point, and then if you have a better understanding or measurement of Higgs waves, you have better. So here we just take whatever available, the best sort of parameter, maybe something almost touch the neutrino flow. So now, then you notice is the dark matter mass between this here and 450 GeV is ruled out. But then what if the dark matter mass indeed turned out to be in this region? Then you say, well, this particular model is ruled out. Then you say, well, can we recover this region by some other type of model? Well, I will come to that here. So this is a question we asked, and then we found say, well, you can maybe you give a little more complicated model. Then you say, well, maybe I have a 2 Higgs doublet, and then this is what happened. But now, of course, 2 Higgs doublet model, you have many versions, and for this purpose, except type 1, which is just scaling down the coupling or raise up the coupling of the standard model Higgs. Whatever the conclusion I dropped it before is a similar. But then the other guys will be different. So we'll take this one for a little bit more analysis to find out what's if we can recover some of the range of parameter space. The type 2 is just one of the Higgs give upward mass, and another Higgs give down type of hot mass. Okay, so in that, so this is the Lagrangian you have. To realize this, then you can introduce Z273 something. But then, of course, this Z273 is different than the one imposed on the D Z273. So you have this. Now, what might change? Well, there are several ways things change. First of all, you have the Higgs dark matter sort of interaction with the Higgs changing, because then you have 2 types here. Well, this also self-coupling, and the mass state is similar to the before. So this change. If this change, that means maybe the relative density, the coupling, and the direct detection in coupling may be different. Before is the same parameter, determine everything. And also the coupling to up quark and down quarks are different. Well, this is still the Higgs part. So you can work in the basis of where one of the Higgs has a wave, another Higgs doesn't have a wave. They can do that sort of thing. Then you can rewrite the coupling of how this here, see, dark matter annihilate into Higgs and 2 Higgs or 1 Higgs. This is something like this here is something like before. So then you notice that many more combinations, but then you can of course lump them together to get something. Okay, and then also the coupling and to W and Z also they will change to up quark and down quark also changing. So that means you can have an up quark and a down quark very differently. So before, if you normalize it in this case, they are the same. So you can do the calculation to get whatever I found. But then now you have to separate the calculate the U quark and the D quark contribution. Then you can parameterize whatever this Higgs coupling to nuclei, which is important for directed detection. Then you find you have for proton go like this, coupling to neutron go like this. Okay, I separated proton and neutron is because in a given nuclei you have a different number of proton and a different number of neutron. So that then if they are coupling differently, because this here allows these guys to vary, so that they can have a different strengths. Then it will change the way you treat before. Okay. That's right. Basically, then detection. Sorry. The relative density is going from here. The annihilation, but then for detection, it goes like this. So the calculation is more complicated than before. And also, the detection have before just one of this. So now you have two of them. Then you can sort of maybe have a calculation and happen here instead of different combinations. But then just the amount itself, you already notice you have different sort of these guys depend on which Higgs you are talking about. Then you can adjust alpha, beta, and then vary these. Okay. Now, once you do that, and then so you can realize whatever this isospin violating coupling of dark matter to nuclei. What this is becoming important is before there was some claims you have seen dark matter candidate gamma, CDMS, and then because all these guys are using xenon, so they have a different target. So the neutron and the proton in there are different. So that means if somehow the proton and the neutron, if they are equal, if they are not equal, then you might have a different sort of cross-section. For example, you take the proton and the neutron proton ratio like this. So then you can, like somewhere you have a cancellation and then the same thing. So then this here, previously people say, well, okay, maybe I can then do something, and xenon is cancelled. But then why not cancel to zero? Because you isotope in xenon, and then you cancel this one, the other one still left something, the other one left something. So you don't completely cancel, but then cancel to the minimum. So, but then with the X and the Lux result, and then this really completely rule out this possibility that gamma CDMS result consistent with the xenon experiment. So I think if you talk about to the xenon guy, they say, well, in this type of scenario, gamma and CDMS just forget about them. They are not there. Okay, so. But now, of course, now the new experiment in southern hemisphere trying to repeat the gamma result, say if that region can be like similar type of experiment also roll out. But then the point here is now this is X, Lux, and then rule out this idea. Okay. This is the same figure. But then, of course, now you have to redo your fate to Higgs talked about, compare with experimental data and say what is allowed parameter space for dark matter mass and the cross-section. To do that, then you have to fit the Atlas CMS sort of couplings to W, to Z. You have to satisfy this range. And then if you do that, then you can find out what is allowed parameter space beta, alpha, and beta. So it turns out that these are allowed sort of range. So then next, you fit the relative density, fit the detection, and you have to work with this region. And also, you have some constraints on the parameter space in the Higgs potential, and then you have the permittivity, right? You don't want your coupling to be too large, so such that the perturbative calculation doesn't work. You also want your vacuum stability to be there, so you consider all this. Then you can also have some constraint on the parameter space. Okay. So now, once we do that, then we say still you have too many parameters. So you have lambda capital H, lambda small h. So the small one corresponding to the standard model like Higgs. The capital H is the one like much heavier. So you do that, still you have this alpha beta within the allowed range. I just show you. You can take some representative numbers. And then we also try to say, oh, okay, maybe it's very much like ISO speed conserving sort of interaction, a little bit of violation, and then very violated like xenophobic type of interaction. So you take this, and then the point is here we want to show you. So, well, okay, so these guys are out of oppression, and then you say, well, if I look at this one. That now this here is route the higher end is only about 90 GeV or so. So 450 become 900 GeV. So that means you recovered this type of range. But then this side, you said that this is still in contradiction. This one here. And then you say, well, maybe I take it to this one or this one. Then you can go lower, right? So you can go lower here. And this is similar sort of thing. But then, so the conclusion essentially say, well, here I can recover all the regions ruled out for the simplest one. But then, of course, if you do it, this is another type of scenario. Say, well, the standard model like Higgs doesn't really contribute to any dark matter sort of say relative density detection. Just the heavy guy is doing the job, right? So then you can take this sort of parameter, or just again to demonstrate what are the possible availabilities you have. Again, you can move it down, right? So now, before for the standard model like Higgs doing the job, then there's a constraint of about 60 GeV. Below that is not allowed because standard model Higgs cannot decay to 2 dark matter, which increase the invisible weight. So that's ruled out. But then this time, if you say, well, for the heavy guy doing the job, the light guy doesn't do the job. So maybe this side is totally allowed. Everything is not. But then it turns out, as I said, you need to consider conductivity, vacuum stability, unitarity sort of thing. Then you find this line. If you cross this line, you have a problem with all the one of the things I listed: unitarity, conductivity, maybe vacuum stability. So this line is ruled out. So that means from here, above is not allowed. Below is allowed. So in that case, you always find maybe about 90 GeV is still allowed. So the 2 Higgs dark matter model, you can recover some of the space, but then you cannot recover all spaces. So below Higgs dark matter mass below 60 GeV or so is ruled out. And then if it's the heavy Higgs is doing the job for dark matter relative density and detection, about 90 GeV below is ruled out. So, so I come to my conclusion. The simplest dark model below 45 GeV is ruled out. And then you can say, ask why I want to recover some of the parameter space, the 2 Higgs dark matter model. Then you find you can recover some of the parameter space. For example, if light Higgs is doing the job, 60 GeV below is ruled out. But then if you do, if the heavy guy is doing the job, below 100 GeV is also ruled out. So we still have a lot of parameter space to probe, and so we have wish to have more experiment going on, provided new data. We'll see what happens. Thank you.
Questions or comments?
Have you considered the mass range of the pseudoscalar A?
Sorry, what math?
A. There's a pseudoscalar A.
No. So in this case, doesn't do anything because pseudoscalar is apparently negative. 2 dark matter apparently conservative, so you don't have that copy, so you don't have any information.
Any other questions? Or everybody is eager for lunch?
Does it help for any the phase transition region like biodialysis or other things?
Okay. So this here, so this is what I'm saying. If I satisfy all these conditions, there are still aerospace or biogenesis. These are several conditions. One of them is first order phase transition. So with these constraints, you still have aerospace allowed. But then CP violation in this case is a problem. In this particular sample one, type 2, we don't have additional CP violation in source, so I cannot do that. But then I can get first order phase transition.
Okay, let's thank Xiaogang and all the session speakers again. And let's have lunch and come back at 2.
Managed to stay on time today. More or less, 5 minutes.